Hey friends, in the previous lecture we derived this equation wherein tau was equal to Vq by Ib, where V was the shear force acting at that cross section, shear force, B is the breadth of the beam, and I is the moment of inertia. Sorry, I-N-E-R-T-I-A. And Q is called the statical moment. Now what is the statical moment? Let us assume that we have some kind of a cross section like this, and this is my neutral axis, and I considered this elemental block, the shaded portion, and I considered some strips, and let this strip be of area dA and of length suppose dy and of breadth suppose b. Right. Now what is Q basically? Q is nothing but, now this is at a distance y1 from the neutral axis, this block, and its height from the neutral axis is h by 2. This height is h by 2. So Q is essentially y dA y1 to c1, that is h by 2 here. Now dA is nothing but is equal to b dy, so y dy y1 to h by 2, or essentially by square by 2, and if we place h by 2 and y1, it will be h square by 8 minus y1 square by 2, or b by 2 is equal to h by 2 minus y1 and h by 2 plus y1. Now, what is the physical significance of this statical moment? We have this elemental block and we considered equilibrium of this elemental block. Now, the statical moment will give us the moment of this elemental block with respect to the neutral axis. So essentially, Q will be the area into y2, where y2 is nothing but the distance of the center or the centroid of the neutral axis from the CG of this elemental block, and therefore this suppose is y2. So area is nothing but is equal to, if the total is h by 2 and this is a y1, so this is h by 2 minus y1 into b, which will give me the area, and y2 is nothing but is equal to y1 plus this by 2, and this is nothing but h by 2 minus y1 by 2. So this is my Q, and this is equal to h by 2 minus y1 into b into, this will be y1 by 2 plus h by 4, or it will be equal to b by 2 h by 2 minus y1 into h by 2 plus y1. So this is what represents the statical moment for a rectangular cross section, and it will be obviously different from in the other cross sections, right? So now we are in a position to summarize the thing. If we have this kind of a beam, and it is acted by certain forces, and if we consider this section and say that Vx try to find out Vx for this section and try to draw this cross section here, then essentially, or I should make it look like this. If this is my cross section, and if this is suppose M, N, and here I am drawing Mn, then essentially the shear stress will look like as tau is equal to Vq by Ib, and Q is nothing but is equal to V by Ib into 1 by 2 into B into h by 4 minus y1 squared is this, right? So BB cancels out, and V by 2i h by 4 minus y1 squared. So essentially, when y1 is equal to 0, you have tau to be equal to tau max, wherein it will be equal to Vh by 8I. When y1 is equal to h by 2, you have tau to be equal to 0. And from here we see that the shear stress across a cross section is some kind of a parabolic function because of y1 squared. So essentially it will be a parabola like this, wherein at the ends we have zero shear stresses, and at the middle or the neutral axis we have the maximum value of shear stress, and that will be given by Vh by 8I for a rectangular cross section. So the shear stress will be some kind of a parabolic function with at the top the shear stress being 0, and at this point it's having its maximum value. And as we have seen also, the normal stress will be some kind of a function like this, where if this is my sagging moment, then normal stress will be, the top portion will have compressive force and the bottom portion will have tensile force. Right. And here at the neutral axis, the normal stress is 0, and at the top it's equal to sigma max is equal to m by I into y, or I should write it yc. Right. So this is the brief summarization of